Good morning, kidlets. Today we're going to talk about some projectile motion problems, specifically two problems that I call classic problem number one and classic problem number two. And learning to solve these problems and the procedure you go through to solve these problems goes a long way towards making you expert at solving these problems. In fact, almost every projectile motion problem can be considered either classic number one, classic number two, a combination of the two, or a variation of one of them. And so what we're going to do today is I'm going to show you the procedure. The basic procedure is that we are going to draw a picture. In the case of classic number two, there's an extra step where we have to componentize or take components of something. Then we are going to fill out the list of knowns and unknowns, and it's a 9-part list, excuse me. And then we're going to solve the y direction using an equation to find time, even if it's not asked for. And we're going to then solve the x direction to find the final distance, which is the most common thing. Okay, so that's the procedure we're going to use. So let's start with classic number one. And classic number one is a horizontally launched projectile. From a high place. After all, if it was horizontally launched from the ground, it would immediately hit the ground and we wouldn't really have projectile motion. The example I'd like to use today is I'd like to talk about a stunt that I saw in I think it was a James Bond film. Anyway, somebody was being pursued by people who were shooting at them or something, and the camera is following this person and they just run off the edge of a cliff. And then the camera pans down and you see that there was a boat in the water waiting for this person. I'll put a little engine on it or something, waiting for this person to get away. So this person is going to hurl themselves or just run horizontally off the cliff, no up and down jumping, and then they're going to have a parabolic trajectory and land in the water over here. And what I'd like to know is what is this distance? Because if I'm the one designing this stunt for the movie, I need to place a boat in the water, but not where the person is going to land. That would be bad. Now let's put some other numbers on the problem to make this interesting. This stunt person is a pretty athletic person, and they're going to run at 8 meters per second. That takes some intestinal fortitude to run at 8 meters per second right off of a cliff. And this constitutes a pretty good drawing. I seem to be running over my tripod here. But what's missing is the coordinate system. And by agreement, we're going to put the origin where the object starts. That is the spot where the person just leaves the cliff. And we're going to make positive downwards and positive to the right for the x and y dimensions. Now, this choice of positive downwards does bother some people, but it's a really good one in this case because the entire problem happens below the launch point. And so that means that all the y numbers will be positive numbers. Okay, now that we've gone ahead and done that, it's time to fill out the list of knowns and unknowns. Remember, this is classic number one. We do not need to break anything into components. And so the first level of the list of knowns and unknowns are the final positions in x and in y. So I asked, do you know where this thing will be in x at the end of the problem? And then the answer, of course, is no. That's what we're looking for. Oh, I have to tell you one more piece of information. Geez, this was almost a nightmare. This cliff is 15 meters tall. It's a pretty tall cliff, 45 feet or so, I think. So now we know that the final position when the person enters the water is going to be 15 meters. The next level of the knowns and unknowns are the initial velocities in x and y. Do we know how fast this person is going at the beginning of the problem in the horizontal direction? And the answer is yes, it is 8 meters per second. Do we know how fast they're going in the vertical direction? The answer is yes, and it is 0 meters per second. That takes a little bit of thought, but if you run horizontally off a cliff in the first instant of the problem, you don't yet have a vertical velocity. Yes, of course you will acquire one. Gravity is going to accelerate you, but there you go. The next level of the knowns and unknowns are the final velocities in x and y. Do we know the final velocity in x? And some people would say, no, you don't. But I'm here to tell you that you do. The final velocity in the x direction is equal to the initial velocity in the x direction. And that is because the acceleration in the x direction is 0. There is no gravity in the x direction. The horizontal dimension doesn't have any acceleration. Therefore, any velocity will remain throughout the entire problem. In the y direction, however, we don't know how fast this guy is going to be moving. Ooh, I assumed it was a guy. What if it was a female stuntman? Don't know. Acceleration in the y direction. Now, this acceleration comes from gravity. And so the number is 9.8 meters per second squared. You know, there's a lot of people who want to put the 9.8 in for a velocity, but it isn't a velocity. Its units are meters per second squared. It is an acceleration. But we need to ask ourselves, is this going to be positive or negative? Because a lot of times this number is negative. But with my choice coordinate system being downwards positive, gravity is pulling in the positive direction. Therefore, the acceleration will be in the positive direction. And finally, the time is unknown to us. This is the list of knowns and unknowns. The most difficult part of the problem and the most critical part of the problem is to get this list filled out correctly. Once you know what you know and don't know, it's time to do some work. And the work, and I'm going to go over here and start up here. The first thing to do is to work in the y direction and try to find the time. So we need an equation that has time in it, so the no t equation won't work. And I found that the Swiss Army equation is usually the best one to use. Now you might ask, why don't we work with the x equation and just directly find x? I've tried that before, and this 0 is constantly multiplying x, and that causes x to leave the equation. And of course, if x isn't in the equation, you can't use that equation to find x. So the best technique is to use the y to find the time, and then the time to find x. One more thing about that. There's a physical reason why. This problem is over when you hit the water, which is a function of your vertical position. So in some sense, y controls this problem. And during the time that you're falling, controlled by y, you are simply moving to the side at 8 meters per second. So knowing that time is going to be important. That's why we're going to solve the y Swiss Army and find time. I wrote out the y Swiss Army equation in its unadjusted normal form. This is really good for your brain to practice with these equations and also to make sure you didn't forget the square, but also for grading. If the grader sees you write this equation, the grader is going to give you a point because they know you've chosen the right equation. Now let's put the numbers in. Y here is 15. VIY is 0, and that multiplies t. And then we have 1/2 of 9.8 times t squared. And although there's a t and a t squared, this does not turn into a quadratic equation because 0 times t is 0. Therefore, 15 equals, and half of 9.8 is 4.9 t squared. So 15 over 4.9 equals t squared. And the square root of 15 over 4.9 equals t. And I have to go grab my calculator. Here we are. And let's do that. Starting with 15 divided by 4.9 equals, the square root of that answer equals 1.75. So this person will be in the air for 1.75 seconds. Quick check, is that a reasonable time to be falling? Yeah, although in movies they tend to run these sequences in slow motion to milk the money they spent on the stunt and to heighten the sense of danger, that is what it would be like. 15 meters, by the way, is about 1.5 PACs tall. The PAC is 10 meters tall. So the next thing we would do, and I'll go over here to the right to do this. The next thing we would do is we would work in the x direction, and here is the x Swiss Army equation. Although it's not the only equation you could use to do this, it works very well. And I have it's my favorite. Now, x in this case is unknown, so we leave it as x. VIX is 8. T is now known to be 1.75. In fact, we could put 1.75 right here. We could, but let's put it, 1.75. And then this entire second term is 0 because it is 1/2 of 0 times 1.75 squared. Almost ran out of room there. So this entire term over here, that turns into 0, and all we're left with is 8 times 1.75, which, according to this, I can just go times 8 equals 13.997, so let's call that 14. So this stunt person is going to enter the water 14 meters away from the edge of the cliff on a 15-meter cliff and an 8-meter-per-second run. So I'd like to put the boat a meter or two beyond that. I don't want there to be any risk that my stunt person hits the boat. And now that we know this number is 14, we seem to know just about everything from our list of knowns and unknowns, except for this final velocity. And I think that the stunt person would be interested in knowing what that final velocity is. So let's go ahead and find it. Let's go ahead and find that final velocity. I'm going to use, first of all, you have to use a y equation to find it because it's the final velocity in y. I'm going to use this one, which is the definition of acceleration, mainly because it is the one with the least stuff in it. It's the easiest one to use. So VFY is going to be 0 plus 9.8 times 1.75. This green pen is very wiggly. So let's do this and clear. 9.8 times 1.75 equals 17.15. So in addition to the 8 meters per second of horizontal velocity, do you want to just call this 17? Yeah, let's just call this 17. We have now acquired 17 meters per second of vertical velocity. If you want to know how fast the person's really going as they enter the water, you need to combine these two, not by simply adding them, but by realizing that they form a vector pair, that there is 8 meters per second of horizontal velocity and an additional 17 meters per second of vertical velocity. And we need to find this hypotenuse right here. So we're going to use the Pythagorean theorem to find the final velocity that's not in x or y, but is in the direction that the person is going. You could also find this angle. Let's just quickly Pythagorean this thing and see what happens. So we need 8 squared plus 17 squared, and then we need to take a square root of that number to get 18.78. Let's call that 19 meters per second. 19 meters per second. And that's the speed he's going to be going when he enters the water. The stuntman might want to know that because at a certain point, that speed becomes too great to survive. And, you know, when you jump off of something that's tall enough, you can be knocked unconscious and drown when you hit the water, or you can be injured to an extent that you will not have a good day. So I know this is all very crowded with this piece of paper here, but I wanted to have it on one piece of paper. But just let's walk through this again. We drew a picture with a coordinate system. We filled out the list of knowns and unknowns. We solved a y equation to find the time. We solved an x equation to find the distance. And then for gravy, we solved a y equation to find the final velocity in y. And I showed you how it gets put back together with the x velocity that's constant throughout the problem to give you your final velocity. If you were an Olympic diver doing this and you wanted to leave no splash, you would have to align your body along this vector so that you got the minimum splash. Okay, I'm going to call this one for now. This is how to solve classic number 1, and then we're going to pick up with the next video on classic number 2.